In this video, I am going to walk you through the calculations for the titration of an acid. You are going to do the calculations for titration of the vinegar with a strong base, and your base is sodium hydroxide. There are a few things that are given to you. The molarity of the base is given and is the same for all three trials. And the volume of the solution, the acid solution, is the same for all three trials, and it's 25 milliliters. Now, in the pictures, you're going to get the initial burette volume for trial 1, 2, and 3. And what you'll find is that the final burette volume for trial 1 will become the initial burette volume for trial 2. And the final burette volume for trial 2 will be the initial burette volume for trial 3, and then the final burette volume for trial 3. These are the initial and final volumes, and so to figure out the volume of the base that you used, you're going to take the final minus the initial to give you the volume of the base. You will have three different values in milliliters for the volume of your base. Then this is what your lab report is going to look like. Question 1, determine the average molarity of the acetic acid solution using this formula over here, where you have the molarity of your acid multiplied by the volume of your acid is equal to the molarity of the base times the volume of the base. We said that the molarity of the base is the same for all three trials and is given to you as 1 molar. The volume of the base is going to be the volume of the base used in trial 1, 2, and 3. And you're going to calculate it. It's going to be row 3 here. We also said the volume of the acid is going to be 25 milliliters for all three trials. Then you have one unknown, and all you have to do is solve for the molarity of the acid. You will have 3 different values for that molarity. Okay, and this is the reaction, right? This is acetic acid. When placed in water, it will partially dissociate. It's a weak acid to give you acetate and H3O+. Part 2. Given that the equilibrium constant at room temperature for acetic acid is 1.8 times 10 to the minus 5, and given the concentration of your acid that you determined in question 1, so that molarity of your acid, determine the concentration of the hydronium ion at equilibrium using the equilibrium expression for this reaction given below. And we have practiced how to do these. To write an equilibrium reaction, we will do products, so the concentration of your products, of the concentration of your reactants, multiplied together and raised to the power of the coefficients that's in front of all of them. Note that the liquids, pure liquids or solids, do not appear in equilibrium reaction expressions. So the products are these two. The concentration of your H3O plus multiplied by the concentration of your acetate, CH3CO minus. They're both raised to the first power because all the coefficients are 1. They're all 1-to-1 ratio. So the power is 1 and we don't write it. You have no more reactants, so that's the only two that are going to be multiplied together. And then all of that is divided by the concentration of your acetic acid from part 1. Note that, as I said earlier, water does not appear because it's a pure liquid. Now, we don't know what H3O plus concentration is, but we know that these two are going to be equal to each other. It's similar to, and I always bring this up, and I think most students roll their eyes, but it's just a simple illustration. Like when you go to the prom and you have 10 couples dancing, so that's your original acid. Well, if some of the acid, so 2 couples decide they are done dancing, they're gonna stop, then you'll have 2 boys and 2 girls if those 2 couples are going to stop dancing, because they're going to split from the original couples. The same idea here from the acid, right? H3O plus and CH3CO minus come from the original acid. And since they both come from the splitting of this acid, both of those concentrations are going to be equal to each other. Everything is a 1-to-1 ratio. And even though I don't know what those concentrations are exactly, I know that they're going to be equal to each other. And if I call H3O plus X, then CH3CO minus is also going to be X. So I have X multiplied by X to give me X squared, divided by the concentration of my acid that I found from part 1. And this is equal to 1.8 times 10 to the minus 5 because the problem gives me the equilibrium constant for acetic acid at room temperature. Okay, so we have the concentration of H3O plus equal to the concentration of CH3CO minus, and they're both equal to X. And therefore, we have X times X equals X squared over the concentration of your acid from part 1 equals 1.8 times 10 to the minus 5. Then solve for X squared, right? You take this number multiplied by your acid, and then you take the square root of that to figure out X, which is going to be the concentration of H3O plus. Part 3, calculate the pH of the sample by using the concentration of H3O plus from part 2. We solved, or you're going to solve, for the H3O plus concentration in part 2. Then you take that concentration and you take the minus log of the concentration of H3O plus of that number in your calculators to give the pH. Remember that the pH is going to be somewhere between 1 and 14. So if you've done it correctly, you'll get a number between 1 and 14. If you get something else, then you must have made a mistake. Make sure you know how to calculate pHs when you are given the H3O plus concentration. Then, for part 4, you are to calculate the moles of the acetic acid in your sample using the molarity of the acid from question 1 and the volume of the vinegar sample. Make sure you convert it to liters. The volume of the vinegar sample, remember in slide 1, it was given to you as 25 milliliters. Make sure you convert to liters. Divide by 1,000. So here's the formula for molarity. So molarity, which is the value from part 1, will go here, and that's equal to moles of acetic acid over the liters of vinegar. And then to find the moles of acetic acid, you multiply the molarity by the volume. You will have 3 values for the moles of acetic acid because you have 3 trials. Then, to calculate the mass of acetic acid in vinegar, using the moles from part 4 and the molar mass of the acetic acid. So calculate the molar mass of acetic acid and then convert the moles from part 4 and the molar mass, right? So use the moles from part 4 and the molar mass to convert to grams of acetic acid. Remember, if we go from moles to grams, we multiply by the molar mass. Part 6, you are to calculate the mass of the vinegar sample by using the volume of the vinegar and the density, which is given to you. Remember that mass is equal to density times volume, right? Volume, in this case, since the density is in grams per milliliter, you don't need to convert to liters. The volume, once again, is given to you as 25 mils, at the first page, on the first page. So use that volume with multiply by the density to get the mass of the vinegar. Note that you will only have one value for this because the volume for all the samples is the same. So you don't need to do this 3 times because it's the same calculation. You have the same volume and the same density. So just do it once. For part 7, then, you calculate the mass percent of acetic acid in vinegar. Here's the formula for mass percent. Take the mass of acetic acid that you calculated in part 5, question 5, divided by the mass of vinegar from 6, multiplied by 100. Your grams are going to cancel because you have grams on top, grams at the bottom, so that unit cancels and it's going to just be a percentage. Then you are going to calculate percent errors for both the mass percent and the pH. Okay, so this actually is supposed to be the mass percent error because the mass percent is in percent, and then you're going to calculate the percent error. So compare the value from question 7 for the mass percent of acetic acid in vinegar and compare it to the actual value of 5%. And by now you should know how to do that because we've done it in every lab where you have the literature value or your actual values, same thing, minus the experimental value, which you found in part 7, divided by the actual value times 100. Make sure that these are reported as positive numbers. Then the pH percent error. So you have the value from part 3, that pH, compare it to 2.3 using the same formula. And lastly, name at least one possible error that could be made during measurements. Now think about where you are making the measurement and how could we make a mistake when we actually take those measurements.